À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Allumage EAP, décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Imagine standing in a dark field at night, far from city lights, looking up at the stars. What you are seeing feels immediate, as if the universe is happening right now. But it isn't. Every point of light in the sky is a message from the past. Some of those messages began their journey millions, even billions of years ago, long before Earth existed, long before humans learned to ask questions about the universe. Now imagine a machine designed not just to observe space, but to capture those ancient messages. A machine so sensitive it can detect heat from objects colder than ice, so precise it can see the faint glow of the first stars that ever existed. That machine is the James Webb Space Telescope. James Webb is not simply a more powerful version of earlier telescopes. It is a scientific time machine. A golden mirror floating in deep space, built to answer questions that humanity has asked for thousands of years. Where did the first galaxies come from? How were stars born? Do planets around other stars contain the ingredients for life? To answer these questions, scientists had to build the most complex and ambitious space telescope ever created, and then unfold it perfectly, millions of kilometers away from Earth. NASA's James Webb Space Telescope is preparing to begin its mission of discovery. By observing infrared light, Webb will be able to look through dust to see stars forming inside of nebulae. It will also allow scientists to observe farther back in time than previous telescopes. More distant objects in the cosmos are more highly redshifted. That means their light shifts from ultraviolet and visible wavelengths into the near-infrared. This shift in wavelength means observations of distant objects, such as the first galaxies that formed in the universe, require a telescope specialized in collecting infrared light. While Webb will explore the cosmos in infrared light, Hubble will continue its observations of the universe in visible and ultraviolet wavelengths. Since 1990, Hubble has completely changed our understanding of just about everything. From galaxy evolution to gravitational lensing and dark matter. From exoplanet atmospheres to our own solar system, Hubble continues to teach us something new about our place in the cosmos. The scientific community is incredibly excited to have these two highly complementary observatories operating together. With their collaboration, they will push the boundaries of knowledge on the backdrop of a rapidly evolving astronomical landscape. A wealth of multi-wavelength and now multi-messenger astrophysical observatories, from space and from the ground, are currently operating or being planned. Hubble and Webb will work together to advance our collective understanding of the universe, ushering in a new golden age of astronomy. The most prominent and beautiful part of NASA's James Webb Space Telescope is its gold primary mirror with a smaller secondary mirror suspended out in front. The Webb telescope is a reflecting telescope, technically an anastigmat telescope. This means that its concave primary mirror captures the light and reflects it to the secondary convex mirror, which reflects the light back to the concave rectangular-shaped tertiary mirror and then finally to the flat fine steering mirror, which sends the light through a hole through the center of the primary mirror to focus on the science instruments behind the primary mirror. This specific optical layout provides a broader field of view while reducing image distortion. While the first two mirrors function like a standard Cassegrain telescope, similar to Hubble, it is the addition of the third powered mirror that classifies Webb as an anastigmat. Webb's primary mirror is the largest ever launched into space, spanning 6.5 meters, or over 21 feet. It is specifically engineered to capture the incredibly faint light traveling from the most distant objects in our universe. Because of its massive size, the mirror presented a major engineering hurdle. It was too wide to fit inside any available rocket. To solve this, the mirrors were designed to be segmented and folded for launch, requiring them to be precisely unfolded and aligned once in orbit. Webb's mirrors are made out of a rare metal called beryllium, because this chemical element is very strong, lightweight, and virtually ceases changing shape when it gets really cold. Starting from beryllium mines in Utah, the mirrors crisscrossed the country. The beryllium was made into a powder of microscopic spheres, then fused by intense pressure into solid discs that were machined and polished. Lastly, the mirror segments were coated with a thin layer of pure gold, less than 100 atoms thick, to best reflect infrared light. All of the mirror machining and polishing was done at room temperature. Because beryllium changes its shape with temperature and only becomes stable at very cold temperatures, the mirrors are manufactured to precisely the wrong prescription at room temperature, so that they have precisely the right shape at operating temperatures. That's negative 388 degrees Fahrenheit, or negative 233 degrees Celsius. That's colder than the surface of Pluto. A robot-like system perfectly mounted each mirror onto Webb's composite backplane structure. Behind each mirror is an actuator system that can move each mirror segment precisely in every direction, as well as modify each segment's shape ever so slightly, so that all 18 segments can be aligned to form a single perfect mirror. After Webb is deployed, it takes several months for the instruments to cool to their operating temperature. During this time, engineers on the ground will use Webb's near-infrared camera and a process called wavefront sensing and control to align Webb's mirrors. The mirrors will be retuned as needed during the mission to maintain Webb's perfect vision. Once Webb launches and the science team aligns those extraordinary mirrors, a new scientific era will begin. A million miles from Earth, NASA's James Webb Space Telescope will look into the early universe for traces of infrared light. One side of the telescope will face the endless reaches of deep space, a void characterized by cold so extreme it hovers just above absolute zero. The other side faces the sun, enabling the telescope's solar panels to drink in sunlight and provide power for all of Webb's systems. Separating these two extremes are 5 stunningly delicate layers dividing endless day from eternal night. The sun shield blocks heat from the sun, Earth, and moon from Webb's mirrors and instruments. Each of the layers is made out of a material called Captain that has been coated with aluminum. The 2 hottest layers, the ones closest to the sun, have an additional layer consisting of a special silicon that gives them that pinkish tint. The coatings are then electrically conductive so that the layers of the sun shield can be grounded to the rest of the telescope and not build up a static electric charge. The thickest sun shield layer is 0.02 of an inch, or 0.05 of a millimeter thick, a clue to the extraordinarily delicate nature of this remarkable structure. In terms of surface area, each of the layers is as large as a tennis court, creating a gigantic challenge to get it into space. Engineers developed a release system to carefully unfold and control the ultrafine sunshield layers in space. Special stitching on each layer, called ripstops, prevents the possibility of a tear spreading across the sunshield layers. Once unfolded, Webb's sunshield becomes a parasol, protecting precision instruments from unwanted heat and opening a pathway to the instruments to cool to the supercold temperatures of deep space. And this enables the pursuit of some of the biggest scientific questions. The James Webb Space Telescope is not in orbit around the Earth, like the Hubble Space Telescope is. It actually orbits the Sun, 1.5 million kilometers away from the Earth at what is called the second Lagrange point or L2. What is special about this orbit is that it lets the telescope stay in line with the Earth as it moves around the Sun. This allows the satellite's large sun shield to protect the telescope from the light and heat of the Sun and Earth and Moon. It took roughly 30 days for Webb to reach the start of its orbit at L2, but it took only 3 days to get as far away as the Moon's orbit, which is about a quarter of the way there. Getting Webb to its orbit around L2 is like reaching the top of a hill by pedaling a bicycle vigorously only at the very beginning of the climb, generating enough energy and speed to spend most of the way coasting up the hill so as to slow to a stop and barely arrive at the top. The James Webb Space Telescope or Webb has once again expanded the boundaries of our observable universe. Its latest triumph is the confirmation of a galaxy named MOM Z14, existing only 280 million years after the Big Bang. This makes it the most distant galaxy ever discovered, observed at a redshift of Z equals 14.44. This discovery offers a window into the universe's formative years and clues about how the first galaxies emerged from cosmic darkness. When the James Webb Space Telescope began observing the early universe, astronomers noticed a population of unusually compact and red galaxies, known as little red dots. Their properties did not match what models predicted for that era. A recent study suggests these objects may be a transitional phase linking dense star-forming galaxies to the earliest massive black holes. Closer to home, Webb is sniffing the atmospheres of planets orbiting other stars. It found carbon dioxide and methane on a world called K218b, a Hycean world that might have a liquid water ocean. Even more recently, it detected sulfur in the atmospheres of super-Jupiters, proving that these giant planets form much like our own Jupiter did, even when they are 130 light-years away. The James Webb Space Telescope wasn't built overnight. It is the result of over 30 years of relentless planning and world-class engineering. It represents a triumph of international cooperation, thousands of scientists, engineers, and technicians from 14 different countries coming together for a single goal. The project survived budget crises, technical setbacks, and moments where it seemed destined for cancellation. Yet, it endured. Webb is a testament to what humanity can achieve when curiosity outweighs fear, and when patience outlasts frustration. This mission isn't just about distant galaxies or exotic planets. It is about understanding our own origins. Every image it sends back is a reminder that the universe is older, larger, and more mysterious than we ever imagined. By looking farther into space, we are looking deeper into time. We are learning where we came from, and perhaps, where we might go next. The universe has been telling its story for over 13 billion years. With James Webb, we have finally learned how to listen.